In this video, we will describe how we can determine whether a mechanism is a valid option or not. In most mechanisms that contain more than one elementary reaction, one of those reactions or steps will occur slower than the other steps. We call the slow elementary reaction in the mechanism the rate determining step. You'll sometimes hear it or see it called the rate limiting step. They mean the same thing. That slowest step is going to typically have the highest activation energy. Because of the height of that barrier, it causes that particular step or elementary reaction to be slower than the others. And because it is the slowest step or the slowest process in the overall mechanism, it really regulates how fast the entire mechanism can occur. So the rate law of the rate determining step is the key component in determining the rate law for the overall reaction. This process of slowing the entire reaction process down can be thought of by analogy to traffic. So if you're taking a long drive and you run into a construction zone, what will typically dictate how fast you can get from point A to point B is how fast you can make it through that construction zone. Because the construction zone is limiting how fast you can get through that particular section, it will limit how fast you can get from point A to point B. Now let's look at the reaction between NO2, nitrogen dioxide, and carbon monoxide to form nitrogen oxide and carbon dioxide. It has been found that the rate for this process is second order with respect to the nitrogen dioxide. We do not see any of the carbon monoxide in the observed rate expression. So a proposed mechanism would be that you have two nitrogen dioxides that come together to make nitrogen trioxide, NO3, plus the nitrogen monoxide. This nitrogen trioxide then is the component that reacts with the carbon monoxide to form NO2 and CO2. If you add these two, the two elementary reactions together, you will see that you sum up to get your overall reaction, which is important for your mechanisms. The NO3 here will cancel out with the other NO3. You have an extra NO2 that acts as a catalyst. And so when you add the two elementary reactions together, you end up with your overall reaction. Now, the thing that makes the slow step, the rate determining step, slower is that it has a higher activation energy. So if we look at the entire process, going from our initial reactants of NO2 and CO to our end products of NO and CO2, what happens is we actually have two different reactions. So we have two transition states that are occurring, and hence two activation energies. The larger of the activation energies, this first one, is what will limit how fast the reaction can proceed. In order to get over this barrier, you need sufficient energy. If you have enough energy to make it over this barrier, then in general you have enough energy to make it over the next barrier. So the first step is the rate determining step. Once you get over the first one, you can easily get over the second one. The rate law of the first step that we have here is the same as the observed rate law, which tells us that this is a possible mechanism. It doesn't tell us that this is the correct mechanism, but we can tell that it is a possible explanation for the reactions that are going on. The way that we validate, key part here is we cannot prove the mechanism, but the way that we validate, the way that we say that it is a valid explanation for what's going on, so the way we validate a mechanism, we have to at least meet two primary conditions. The first is that all the elementary steps must sum to the overall reaction. As we saw in the previous example, we had components like the nitrogen trioxide, NO3, which were reactive intermediates. They were first formed and then consumed, so they cancel each other out when we're adding the two elementary steps together. we ended up with our overall reaction when we added the two elementary reactions. So that checked off our box for do the elementary steps sum to give us our overall reaction. The other part to validating a mechanism is that the rate law predicted by the mechanism that is being proposed must be consistent with the experimentally observed rate law. That is what we saw in our previous example, where our initial step involving two nitrogen dioxides coming together agreed with the experimentally determined rate law. There are some additional considerations that need to be made when we're looking at a mechanism and trying to figure out the rate law. When a mechanism contains a fast initial step, the rate limiting step may contain intermediates. And as we have previously said, the rate law for the overall reaction cannot contain intermediates. The rate laws for our elementary reactions, they often will contain intermediates, but when we put them together to come up with our overall rate law, we have to find ways of replacing any intermediates in our rate laws. So when a previous step is rapid and reaches equilibrium, the forward and reverse reaction rates are equal. Because they are equal, the concentration of the reactants and products of one of those steps are related to each other, and the products of these types of reactions are typically intermediates. So we can use that relationship from the equilibrium where the products are related to the reactants. We can use that relationship to re-express the intermediates in terms of the reactants, which gets around our problem of having a rate law that has the intermediates in them. We will look at an example on the next slide dealing with just this sort of situation. By substituting into the rate law of the rate determining step, we will be able to produce a rate law in terms of just the reactants. So let's say we're looking at the reaction of hydrogen H2 with nitrogen oxide NO to form water and nitrogen gas. The observed rate expression is third order overall. It is first order with respect to hydrogen and second order with respect to nitrogen oxide. So a proposed mechanism is we need to come up with a way of accounting for the second order with respect to the NO. So what the proposed mechanism is that we have a fast initial step which rapidly produces a lot of N2O2. This builds up and eventually you get a back reaction which establishes a pre-reactive equilibrium. So this equilibrium, where the rate of the forward reaction is equal to the rate of the reverse, makes it so the two concentrations are fairly steady. The N2O2 then bleeds out, so the concentration slowly dwindles as it reacts with H2 to form water and N2O. The N2O then reacts with another hydrogen to give the water and the N2. This second step is proposed to be the slow step, and the rate law for this particular step would be hydrogen raised to the first power and N2O2 raised to the first power times the rate constant for this particular step. So we get the rate for the slow step is equal to K2 times hydrogen H2 times N2O, both of them raised to the first power. Now the problem that we have with using this for our overall rate is that the N2O2 is a reactive intermediate, and we can't have reactive intermediates in our rate laws. So we need to come up with a new way of expressing this N2O2 in terms of reactants. Well, because this first step establishes an equilibrium, the rate of the forward reaction is equal to the rate of the reverse. So for step 1, the rate of the forward equals the rate of the reverse. We can write out the rate of the forward step, which would be K1 times our concentration of our reactants raised to their respective coefficients. So that's K1 times NO raised to the second power. That's the rate of the forward. The rate of the reverse would be K minus 1. This negative 1 here, a subscript for the K, is what's commonly used for the reverse process. So the forward reaction gets K1, the reverse process is K minus 1. The negative there indicates that it's for the reverse reaction. Okay, so the rate of the reverse reaction is K minus 1 times N2O2 raised to the first power. These two are equal. So we want to have a new way of expressing this N2O2. Well, we can take our K minus 1, divide both sides by that, moving it over to the left-hand side. This gives us our N2O2 concentration is equal to K1 over K minus 1 times NO quantity squared. We can then take this expression here and plug it in anywhere that we see N2O2. So if we take this, if we replace this N2O2 with our expression into what we had for our rate limiting step, right? This is our rate limiting step. We plug in wherever we see this N2O2, our expression, we get this. We can then lump all of our rate constants together. So we just move K1 and K minus 1 over here to be with the other K values, and we get this expression. So this matches with our observed rate law. And what this is telling us is that this K observed is a constant, and this constant is equal to the constant K2 times the constant K1 divided by the constant K minus 1. Because these are all constants, the ratio is a constant, and so our proposed mechanism here agrees with our proposed rate law. Another thing that we need to check is, do the individual steps, when we add them together, do they make our overall reaction? Well, we have our NO here. We have two of those, that matches. This N2O2, we have it here and here. So we have it as a product, then as a reactant, so it's an intermediate. Those two, when we add them together, will cancel out. We have this N2O and an N2O here, so these two will cancel out when we add the reactions together. We now have 2 H2s, so that agrees here. We have 2 waters, that agrees there, and we have 1 N2, which agrees there. So our proposed mechanism is valid in the sense that each one of our individual steps adds up to the overall reaction, and the rate law that we come up with for our proposed mechanism agrees with the rate law that we see. Because these two agree with each other, that means we have a decent amount of confidence that our mechanism that we are proposing is correct. It still could be wrong. There could still be stuff that we aren't seeing, but as far as experimental results are concerned, it is predicting those values correctly. The last thing that we need to look at are catalysts. So catalyst is a substance that affects the rate of the reaction without being consumed. As we said before when we were defining catalysts, you can tell a catalyst in a series of elementary reactions. It will be something that is first consumed, and then you get it back when you're all done. So the catalyst will be involved in your overall mechanism, but when you're all done, you get it back. It is not consumed by the time you get to the final step. Catalysts work by providing an alternate mechanism for reaction, and that alternate mechanism has a lower activation energy, or the pre-exponential term is lower, or a combination of the two. Because it's providing this alternate mechanism, and that alternate mechanism has a lower activation energy or a better A term, it is faster. The catalysts themselves are typically consumed in an early step of the mechanism and then get reproduced back at the end. An example of this is ozone decomposition. So in the stratosphere, ozone will break down over time. So ozone can react with molecular oxygen. Both of these, you will find them in the stratosphere. That is where the ozone layer occurs. So O3 will react with O to produce 2 oxygen molecules, 2 O2 molecules. This process, thankfully, is very slow. The nice thing about it being slow is that allows ozone to build up, which gives us our protective ozone layer. Now, back in the mid to late 1970s, Roland and Molina out in California performed a bunch of experiments looking at some of the data from satellites and determined that the ozone concentration over the Antarctic was actually reducing in size. It took several years, but they figured out that the reason that the ozone concentration was reducing in size was from chlorofluorocarbons, CFCs. These compounds are very stable in the troposphere, but when they get up into the stratosphere, the high energy light, the UV rays that are in the UVA, UVB, and UVC range, actually have enough energy to break the carbon-chlorine bond. The carbon-chlorine bond is fairly stable down in the troposphere, but in the stratosphere, where you have those high-energy photons, those bonds will break, releasing chlorine atoms in the gas phase. The problem is these chlorine atoms in the gas phase can react with ozone to form oxygen, O2, and ClO, chlorine oxide. This chlorine oxide can react with with an oxygen atom to form another oxygen, and you get back the chlorine. So the chlorine can then go up here, react with another O3, another ozone to form another oxygen, another ClO. The ClO comes here, reacts with an atomic oxygen, and forms O2, and you get back your Cl, your chlorine. We call these radicals, but it's essentially a chlorine atom. The fast step is this one here. This one is slow, but it's not that slow. So this is the slower of the two, but it's still a fairly rapid step. The problem is that because the chlorine acts as a catalyst, this will rapidly break down the ozone layer, which is what we have seen. The chlorine radical acts as a catalyst for the catalytic decomposition of ozone, and it is this process here that has led to the formation of the hole in the ozone layer, which primarily happens over the Antarctic, but it has also led to a thinning of the overall ozone layer. So the ozone layer itself is thinner than it used to be. Thankfully, back in the 1980s, the Kyoto Protocols came into effect, in which many nation states decided to stop using chlorofluorocarbons, and so we stopped pumping these chlorine atoms into the stratosphere, and so the ozone hole is actually starting to close. It takes a long time for the molecules in the troposphere to make it up into the stratosphere, roughly about 20 years for that to occur, and so we are really only now seeing the effects of that global effort to get rid of chlorofluorocarbons. So that is an example of how a catalyst can produce a reaction that moves faster by providing an alternate pathway. This pathway here is faster than this one, which leads to the breakdown of the ozone being faster and has caused significant problems.